Hello, everyone. Welcome to this last Mother of All demo days for the year. We have 4 demos today from ProbeLab and CryptoEconLab. And if you don't know what demo day is, it's once every month the Starfleet teams get together to share progress in their projects in the format of a demo. And we are going to start with Guy.
Hi, everyone. I am Guy. I'm working with ProbeLab at ProbeLab. And lately, we've been working on a project that is the effectiveness of the Bitswap Discovery Process. So we dug into Bitswap. So what was the motivation for this project? So at ProbeLab, we want to get rid of as much magic numbers as we can that are inside IPFS. What's a magic number? So it is just a number that is there, and we don't really know, or we don't have a strong reasoning why it should be this value. And so we're chasing them. And Bitswap in particular, so the way it works is when a user or when an IPFS GET request is made, Bitswap will have 1 second to broadcast requests to all of its connected peers. And if it didn't find the block it's looking for within this 1 second, it will start a DHT lookup to find the content providers and then fetch the data. And so today we want to find out if 1 second is actually a good value. And we will also measure whether or not Bitswap is efficient to discover content in general. In order to be able to reason about this, we had to measure Bitswap and measure the IPFS network. So we had to request a lot of CIDs through Bitswap. We got a big list of CIDs just by sniffing Bitswap traffic on the network. And so the setup of the experiment is we give Bitswap 15 seconds to find and fetch the content, which is a lot. And we prevent it to use the DHT. So it's only Bitswap. You can only broadcast to your directly connected peer. You cannot use the DHT to find the content. And in the case Bitswap doesn't find the content within 15 seconds, we will simply verify on the DHT if the content is available or if just Bitswap couldn't find the content because it doesn't exist anymore. We also want to prevent recursive content resolution, which means that if you get the root CID of a block, we don't want to follow up with other blocks that are inside this file because they're likely stored on the very same host. And we run all of the measurement in a Google Cloud VM in a data center in Central Europe. So that's for to explain the latencies that we will have. So the result we got from these studies is that Bitswap was able to discover content on its own in 98% of the case, which is really a lot. So Bitswap alone can find content. So the price to pay is that Bitswap is really flooding the network. It will solicit more than 800 peers and send like 700 messages. So it will literally flood the network, but it will most of the time get the content it's looking for. So now we can see, so the CIDs we took, we think are representative of the IPFS network requests in general. And so out of roughly 50 requests, actually, the top 10 peers provide roughly 60% of all the blocks. So it means that if you're directly connected to only the top 10 providers, you will get a 60% success rate with Bitswap Discovery, which is a lot. And it proves that the IPFS network providers are somehow centralized. And so we can see on the right that so the top 10 peers really provide a lot of CIDs, and a lot of them are operated by NFT.storage. So that represents a big share of all the IPFS traffic. So now we're going to look at the latencies. So as we can see, most of the IPFS requests are resolved within 1 second. So the time that is plotted here is both the discovery time and the fetch time. So the time it takes to discover where the block is stored and to fetch the actual block. And so we can see that some of the requests take, let's say, more time, let's say up to 9 or 10 seconds, but it's very rare. And if we zoom further inside the first second, we can see that there is a high peak in the 201st millisecond. So we have that almost 80% of the successful Bitswap request return in less than 200 milliseconds. Yeah, so it means that Bitswap is fast, Bitswap finds the content, but Bitswap really floods the network, which doesn't scale because if the networks would scale 10x or 100x, we would need to open 10x or 100x connection and maintain them and flood the network with 10 to 100x. And it's just not scalable. So for now, it works, but we gotta do better. And so you will find the complete report available at Discord code that describe the full measurement methodology. I didn't go through all of the detail for time reasons. And we also have just more data and plots and some improvement recommendations. So there is the Move the Bytes working group that is working on, let's say, the next Bitswap. Here we have some recommendation to improve Bitswap. So that can serve of inspiration for future design protocols. And yeah, that was it for me.
Thank you so much, Guy. We will move on over to Dennis.
Cool. Okay. So as some of you may know, we have dialed down the Hydra boosters, but we didn't really dial them down completely, but we only unplugged the database. So what's the background to that? So Hydra boosters in general are just a collection of, so each Hydra booster has a couple of heads, and ProbeLab is operating quite a bunch of them. So all Hydras strive to improve the content routing performance, and ProbeLab is operating around 135 Hydras. And each of these Hydras has a bunch of heads, roughly around 10 to 15. So in total, ProbeLab is operating around 2,000 Hydra heads, which make up around 12% of the network. And the idea is that to distribute those Hydra heads in the hash space such that every provider record that is written into the DHT ends up at least one Hydra head. And this in turn will then improve content routing performance because all Hydra heads are connected to the same database. And if you hit any other Hydra head in a completely different area in the key space, this Hydra head can grab the provider record from the common database and serve it right away. And you save a bunch of DHT hops there. And next to the content routing performance improvements, Hydras also serve as network bridges. And by operating them, they incur a significant cost to ProbeLab. And as we've heard in the previous Starfleet's all-hand presentation, we want to cut them down. So the goal was to save some costs on operating those Hydras, but with the constraint that we want to keep the network bridging functionality. So we cannot turn them off completely, but we need to keep them in the DHT for this network bridging. So we thought how we could decrease the cost, and the idea was to just unplug the database. So all the Hydra heads will stay in the network, but they won't have a common database anymore. So this means they won't store a provider record and they won't serve provider records anymore, and will only participate in peer routing. So they will still point to closer peers to a certain CID, but won't serve any data anymore. So this was the idea. And so the first thing that we did was, so what would be the performance impact of doing that, just unplugging the database? Is it reasonable or is it too much? And for that, we deployed 2 fleets of 6 Kubo nodes into a diverse set of regions, or in 6 different regions. And once one fleet ignored all Hydra heads, so if I request some data, or if I request closer nodes to a certain CID, and the other peer returns some Hydra heads, I will just ignore those Hydra heads and will then take the closest node that is not a Hydra. And the second fleet is just a common and normal Kubo node and operates normally. And those fleets were just issuing a couple of retrievals from the network. So we're just constantly retrieving data from the network, and we were measuring the latency. So how long did it take to find the first provider record to a random CID? And on the right-hand side, you can see the data that we gathered in this measurement. So the blue lines, or so the blue bars are the ones that didn't ignore the Hydras, and the red bars are the ones that ignored Hydra responses. And then each set of bars is the 50th, the 90th, and the 95th percentile. And as we can see that if we ignore the Hydra response, we incur a performance hit. So we can see that each retrieval gets a little slower. But as management has decided, this is reasonable. So we went ahead and dialed and unplugged the database in the back of the Hydra heads. And this happened on the 1st of December. And here we can see, on the x-axis, the date, and on the y-axis, the latency to find the first provider record. And each line is a different percentile. So we have the 50th, the 90th, and the 95th percentile. And these are hourly latencies that you can see here. And as you can also see, starting from the 1st of December, I think it's 5:30 UTC PM, we did the Hydra DB switch, as I called it here. And as we can clearly see, there's like a step, like a performance degradation that's happening here. But how large is that? So we compared our prediction with what we've actually observed afterwards. And so this is the additional black bar that you can see here. And we can see that we underestimated the performance hit a little bit, not significantly, but we underestimated it a little bit. Yeah, we think that skipping Hydras actually saves us a hop in the case when Hydras don't reply with anything anymore. So this could be a reason why it's actually faster if we ignore Hydras than when we don't ignore them, but they just don't reply with anything anymore. So the outcome is we have a 36% 36% cost savings, and the other cost driver for the Hydras is the egress traffic from AWS, which make up around one third of the cost. And there's I did a back of the envelope calculation. I think most of the egress traffic is actually only the handshake, TCP connection handshakes or round trip times and protocol selection, multi-stream select. And so there's probably also some area of improvement. And I've written all of this up with plenty of more graphs in also a final report, same as Guy. And this is linked here, so feel free to have a read there as well. So that's it. So there's this other measurement that we're doing. We're advertising it quite a bit and making some noise for this net hole punching measurement campaign. We're doing a hole punching December, and this December is halfway through. So I thought we could give a brief update of how it's going and see which data we've already gathered. So we started collecting data beginning of November, and then made some noise starting in the last week leading up to December. And here we can see the active API keys per day over time. And we can see that starting on the 1st of December, there were still some people joining the campaign, but it leveled out at around 80 to 90 active clients that are contributing data to the measurement campaign. I sent out around 120 API keys, and actually 272 clients, unique clients, had contacted our server. So those 89 active clients per day could be, they could differ from day to day. And so where are those clients located? So the people that are participating in this campaign, basically on all continents except for Africa. So that's a pity. So if you know someone from Africa, I would like them to join. And but it's a diverse set already. So that's pretty good. Those clients, those people that are running the puncher client had contributed over 3 million 3 million hole punch results. These are not necessarily actual hole punches, but at least they reported if something went wrong, or if something went well here. So these are the hole punch results per hour. Per day. So the y-axis should be per day, and then again over time, it looks similar to the uptake of the active API keys, and so we have around 150,000 results that come in each day from those 80 to 90 clients. That's what I meant. So not all of them are valuable, and I feared that most of them are not. But actually, as I had a look today, those brown line and those this purple line are actually the relevant ones. So these are the failed hole punches in purple, and the successful ones in brown. And this nose here at the right hand side is just a visualization issue. So just ignore that one here. And actually, the minority are hole punch results that are actually irrelevant to us. So these are the important ones, and as we can see, this is the majority of the data that comes back, which is great. So as I said, we have clients in a diverse set of locations, but this is actually only one part of the equation. We can make up for the lack of diversity in our client locations if the remote peers that we actually hole punch are in a diverse set of geolocations, and this is actually definitely the case. So this is the so a common misconception is that the clients hole punch each other, but actually they are just hole punching a random peer in the whole IPFS network, and those peers are coming from all of these countries that you can see here. Keep in mind, some of them may be behind or like running a VPN in a VPN network. But anyways, this is great. This is a diverse set of data points that we get here, which is super valuable for the full analysis that we plan for January. And then probably the most interesting thing, so what's the success rate? And as you can see here, this is around, it wobbles around 70 to 60%, which is a little less than I've observed and reported previously, but only a little less. But this is also expected as we, as we're running it in a diverse, non-controlled environment or non-controlled networks. Beforehand, I was just running it in my home network and in a couple of other networks that we knew, and now we're distributing it to a diverse set. And this also needs some data digging because I may need to filter out some results here which don't make sense. So this is why we have this preliminary batch here on the right-hand side. But this should give you a ballpark in how successful this whole process is. And with that, it's not too late. So if you plan to, or if I want to call out, please join if you want. There are the links. You would need to run if you're on a Mac, you could just run this little icon on the top right. It's a menu bar application. I'm running it here as well. And no technical skills are required, but if you're tech savvy, you can also, there are also command line tools and so on. And please join and participate.
Awesome. Thanks so much, Dennis, for sharing. Last but not least, we have Maria with CryptoEconLab.
So today I'm going to talk about Makeafill. So this is a Python package that we worked on at CryptoEconLab. This package contains essentially a model of the Filecoin economy. So allows users to provide a few parameters that encodes some behavior of storage onboarding, and then based on those parameters, it simulates a few metrics about the Filecoin economy, and in particular is focused on circulating supply. And and the components that make up circulating supply, which is how much fill is being minted, how much fill is vesting, how much fill is being locked, and how much fill is being burned due to gas usage. So this will be a demo. So if things break, it's a demo, so it's fine. And I'm just using here a Jupyter notebook from Google Colab. So we can share the link afterwards and anyone can run it and play with the code. And so here I'm just installing. So this can be installed via a pip, which is a common way for Python packages. And while it is being installed, I'll just say that this is the repository for our code. You have here more information about each parameter, what the parameter means, how to use it, a few examples, and then some references at the end. And we also have here some notebooks that you can run locally instead of just running here on the Google Colab. So it was installed, and now we are just loading the package, which is Mekafill, and a few others that are relevant. And so the first step is defining the parameters for the model. So I'll go over each parameter and what the parameter means. So the first few parameters are related to time. So when do we want to run the simulation? So we need to provide the current date. So this is essentially used for collecting past data that we need to start the simulation. We can also provide a start date, and this means that you can run simulations in a date that is past the current date. And the reason for this is if we want to do some back testing and do scenarios of what the economy would look like in the past, we can have a start date that is later than the current date. If we want to do just forecasting into the future, we need to have a start date that is at most 2 days before the current date. And this is because we need to collect some statistics to restart the simulation. And so once we define the start date and the current date, then we define how many days we want to forecast into the future. And so how many days will be model starting from the current date. Okay, and so here we are just starting at the start of December of this year, and we are forecasting 1 year ahead. The next is what is the daily power being onboarded, and here we are referring to the raw byte power, and this is measured in pips. And there's two options here. You can either give just a single number, as we have here in the example, and if you give a single number, this means that for the entire forecasting period, so this year that you are forecasting in the future, you'll assume that every day this is the amount of new raw byte power being onboarded, okay? But you can also give a vector of numbers. So instead of giving a single number, you can give a list. And here, this means that you have more flexibility. So you can encode other assumptions, like, for instance, imagine that the raw byte power is increasing a little bit every day, or it increases and then decreases. So you can model different behaviors of onboarding for the future. But for this example, we'll start just with the simplest one, which is assume the same level of onboarding. And here we are assuming 10 pips per day. The next one is the renewal rate. So this is the percentage of power that is scheduled to terminate that instead of terminating renews. So when a sector is onboarded in Filecoin, it has a period of time that is being committed. And when that period runs out, the storage provider has the option of just letting the sector expire, or they can renew the sector. And so this is essentially the percentage of raw byte power from the power that is scheduled to expire, how much is being renewed. Okay, so the more power that is being renewed, this means that the more power the network is retaining every day. As with the power here, the second parameter, this one can also be a number or a vector. Okay. And then we have the fill plus rate. So this is the percentage of power that is being onboarded. So from these 10 pips that is being onboarded every day, how much of that power includes fill plus steals? Okay. And again, this can either be a number or a vector. And here we are just assuming 10%. And finally, we have sector duration. So another choice that storage providers have is when they are onboarding the sector, for how long are they committing the sector? And here, this is controlled by these duration parameters. So here we are assuming that all new sectors that are being onboarded, they are being onboarded with a duration of 1 year. And this can only be one value. So you cannot provide here a vector. So it's just all sectors have the same duration. So as you can see, these are all the parameters. So we simplified a lot what type of behavior we can encode in this model to make it as simple to use and interpret as possible. But of course, this is a simplification, right? In the end, you have different storage providers coming in with different durations, different renewal rates. So this is a model that tries to simplify all that into a set of parameters that then you can tweak and run scenarios with, okay? So once these parameters are fixed, then we can just run the model. So here we are using this run simple sim. We are putting in all the parameters we defined, and then the result comes in a data frame, okay? And here I'm just selecting, so this data frame will include more statistics than what is being shown here, but I'm just selecting the ones that I talked about previously. So we have for each day, what is the circulating supply, what is the Filecoin being minted, being vested, being locked, and then being burned. And then we can do some visualizations. So here you can see that we have here the main assumptions of how much power is being onboarded, the renewal rate and fill plus rate. And then we have here all the components for circulating supply. So the fuel that is being mined and vested, they contribute positively to circulating supply. So this means that they are increasing circulating supply, and so they are positive. On the other hand, the fuel that is being locked or burned, they reduce circulating supply, and so they contribute negatively to the final circulating supply. And so we have here, if we add the mined and vested, and then we subtract locked and burn, we get this value for circulating supply for 1 year ahead. And this is all there is to it. You can then use different functions to just model specific parts. So if you just want to see the power being onboarded, or if you just want to see the field that is being mined, we have specific functions. So then if you don't want to run the full simulation, you can dig in and use just some parts of it. And you can also play with different parameters and see what would be the impact of changing specific values there. So for instance, here we have an example where instead of having a renewal rate of 40%, we assume we have perfect renewal rate. So all the sectors are renewing every time. But all the other values are the same. And here we can see that, so it's running the simulation and then building up the plots. You see that it doesn't look very different in terms of my mined fill and vested fill. The big change here is how much fill is being locked. So again, because sectors are renewing more, they are they are not exiting the network, and so that fill that was locked on those sectors is not being released, and so we have more fill being locked, and this decreases a little bit circulating supply. But then we can also have an example here where instead of giving a single value for the onboarding power, for the power being onboarded, we can give a vector. And here we are assuming that we start with the initial 10 pips, and then we grow a little bit every day, okay? And we can see how circulating supply would change. And you can see that when the plot shows, okay, again, here we see now a bigger change. So now we are growing our network even faster. And this means that we are locking even more fill. And this means that the circulating supply then starts decreasing. Okay. And so this is what you can do with this model. You can play with different values and then see what would be the impact on the different components of circulating supply. And once again, if you want to read more about how this model is designed, the main assumptions, you have here the links. You can also go to the to our repo, install it, play with it. And I will want to just finish by thanking Tom and Kieran. They worked a lot on this model with me, and so they are not presenting today. Kieran is here, so if you want to give a shout out, he's here as well. But they were a great help here, so thank you.
Thank you so much, everyone, for attending the last Mother of All demo days. And thank you to all of our presenters. You guys made the last one awesome. But our next demo day will possibly be in February, so stay tuned, and we will look forward to you guys next year. Thanks so much.